Is there anything else that you wanted to tell me? I remembered recording, but I couldn't hear you too well. So is there anything else? Any other doubt? Okay, fine. We will just continue over here. So essentially, if you now have ui, which is an eigenfunction of a, and you can write it that a operating on ui is equal to this number small ai ui, then the question is, would ui also be an eigenfunction of b? Right. So what we did was that, if you remember, we tried this ab operation on ui, and then because we knew that AB is the same as BA, we reversed the order. And finally, we came up with this particular statement that A operating on B of UI is equal to AI B of UI. Okay. And why did we, how could we write this particular thing? We could do it because B is linear, right? Now, if we look at this statement carefully, as I told you, we see that A operating on this quantity or this function B of UI is the same as some number multiplying that same function B of ui. So in other words, B of ui is an eigenfunction of A. More so, it is an eigenfunction of A with the eigenvalue small ai. Now we can take two cases, one where ai is non-degenerate and the other is that ai is degenerate with a degeneracy of n. Now, I hope all of you remember what non-degenerate is, what degeneracy means. Okay, so I'm going to now start off from there. So I will start off with the new page. Somebody else has entered the room, waiting room. So I'm going to just admit them in. Okay, so I will change the page now. Oh, okay, I'm sorry. I still have a spotlight. Okay, let me now change page. Okay, so everybody seeing a blank page? Yes?
Yes, ma'am.
Okay. So now we will start off with the thing of, I will just remind you once again, what do we mean by non-degenerate? Okay. So what I mean by non-degenerate, okay, just one second, somebody else has come in. You really have to stop entering the room so late. Okay. I advise you all to be ready a little in advance. All right. Because otherwise you miss stuff, and it's also very annoying for me to keep admitting people in. But I can't tell actually. Some of you have connection issues, so I will not say anything. Just join. Okay. Right. So what do I mean by non-degenerate? Okay. So by non-degenerate, I mean, suppose you have an eigenvalue ai. Okay, then I will say there is only one independent eigenfunction associated with it. Okay, with it. Okay, so this is the first statement. All right, so there is only one eigenfunction, one independent eigenfunction that is associated with it. Okay, if I say the degeneracy is n, to make it easier for yourselves, you can think of n as a number like 5 or 72, okay, or 1036. Okay, it doesn't matter. Okay, think of it as some positive number. Okay, so if the degeneracy is n, that means with ai there are n independent eigenfunctions associated with it. Okay, right? Now, what do I mean by independent? It means that you cannot write down one of these eigenfunctions as a linear combination of the others. Okay, That is what I mean. Right. Now, let's go back to our statement. What did we? So we are going to take now case 1 where AI is non-degenerate, right? Which means that we are essentially taking this particular case, right? So what was our statement? That A operating on BUI is equal to AI BUI, right? Now, AI is non-degenerate. Therefore, BUI is not linearly independent of UI. Okay, it means that you should be able to write B operating on UI in terms of UI itself. Why? Because there is only one independent function which is an eigenfunction of A with eigenvalue AI. If this is not linearly independent of UI, we should be able to write BUI in terms of UI itself, and I will call that number as BI. Okay? So therefore, UI is also an eigenfunction of B with eigenvalue BI. Okay? Is this clear to everybody? Has everybody understood what I'm trying to say over here? If there are doubts, please ask. Has everybody understood?
Ma'am, please repeat it once, ma'am.
You want it to be repeated. Okay.
Ma'am.
So what have you? Okay, so 1 second, Mohan, don't go on mute, please. Okay. Let me just
Okay, ma'am.
ask you what you have understood. See, did you understand that when A is operating on this new mathematical function B of UI, okay, it
Ma'am.
is again having an eigenvalue AI. Did you understand that?
Yes, ma'am.
That you have understood. So that means this statement you have understood. This statement is clear to you?
Ma'am.
Okay.
But
Is there
please
anybody
repeat.
else apart who has not understood this statement itself? Any confusion with respect to that? Has everybody understood? I know it's after lunch and you're all sleepy, but please make an effort. Has everybody understood this statement?
Yes, ma'am.
Okay, good. All right. That is one more person who told me. She must be the only other person who's awake. Is everybody else awake? Have you all understood? Please.
Yes,
Yes,
ma'am.
ma'am.
Okay, good,
Yes,
good,
ma'am.
good. So this statement thereby everybody has understood. Okay. Now what am I saying? I am saying this AI is non-degenerate. When I say it's non-degenerate, what do I mean? I mean that there is only one linearly independent eigenfunction associated with it. Okay. What do I mean by only one linearly independent eigenfunction associated with it? That if I get any other function which is also showing an eigenvalue of AI, it must be linearly dependent upon this UI. Is this statement clear? Okay. Suppose now I find that I get some psi which is equal to AI psi. Okay. And I know that UI is AI, my mistake, AI is non-degenerate. Okay. That means, what does it mean? It means that this UI and psi are not linearly independent. Okay. If they were linearly independent, then the degeneracy would become 2. I will not be able to say it is non-degenerate. If it is non-degenerate, it means there is only one independent function, which is an eigenfunction of A with eigenvalue AI. Is this clear to everybody? Okay. Non-degenerate
Yes, ma'am.
means if AI is non-degenerate, it means there is only one linearly independent eigenfunction associated with it. Okay. Now, suppose I know that this BAUI is also giving me this eigenvalue AI. Okay. Suppose now I say no, BUI has nothing to do with UI. So then there are two eigenfunctions, right? One is UI, one is BUI. Then the degeneracy becomes 2. But what have I started off saying? I have started off saying this, that it is non-degenerate. If I say it is non-degenerate, obviously BUI cannot be completely independent of UI. If it was completely independent, there would be two functions which have the same eigenvalue AI, in which case the degeneracy becomes 2. But since the degeneracy is 1, it's non-degenerate, right? AI, which means degeneracy is 1. Since the degeneracy is 1, this BUI and this UI definitely have a relation. How will I write that relation? I am writing it like this. Okay. If I write it like this, what you will realize is that this is an eigenvalue equation for B, for this operator. It is telling you that B operating on UI gives a number BI times UI. So thereby UI is also an eigenfunction of this operator B. Is this clear to everybody now? Have you understood?
Yes, ma'am.
Yes, ma'am.
Is it clear? Good. So this was, of course, the simple case. All right, this is the simple case. So now let's go to the more complicated case. So we have dealt with the fact that if AI was non-degenerate, great. Okay, no problems. Now suppose it is degenerate. Okay, so I will change pages both here as well as here. Okay, so let's take now case 2. And case 2 is what? That AI is degenerate. Any doubts? Can you see it? Yeah. And degeneracy is n. Okay, and as I told you, in your head you can put an n as a number like 2, 5, 22, whatever. Okay, yeah, it is one such thing. What does this mean? It means that let us now, there is not just one eigen function, right? There are n eigenfunctions, okay, which are linearly independent, which have eigenvalue ai. Okay, so let us just write it down. So I must be having some ui. Now beside that ui I will write a 1. Okay, then there is a ui2. Okay, there is a ui3. Okay, ui3. Okay, like that there is uin, and it is such that A operating on UI1 gives me AI UI1. A operating on UI2 also gives me AI UI2. Like this, A operating on UIN gives me AI UIN. And these n eigenfunctions are linearly independent of each other. They are all linearly independent of each other. Okay. What does that mean? It means that I cannot, just 1 second, I have to admit some people. Yeah. It means that I cannot pick up, let us say ui2. Okay. So not this, sorry. I cannot say ui2, and it's not possible for me to write it as a linear combination of some, say, c1 ui1 plus c3 ui3 plus cn uin. I cannot do this. Not possible. Okay. So this is what I mean by linear independence. I cannot write one of them as a linear combination of the other two. How would I explain this? If you remember, in three-dimensional space, when you have I, J, and K, can you write I as a combination of J and K? You cannot, right? J and K will only give you position vectors on the YZ plane, right? It cannot give you anything in the X direction, right? So similarly, here I am telling you that these guys are all linearly independent, which means they form an orthonormal set. One of them cannot be written in terms of the other. Is this clear to everybody? Has everybody understood this?
Yes, ma'am.
Okay. Now let's get on to that earlier statement which we had. Okay. You remember what we had come to this conclusion? We had come to this conclusion right here, this statement over here. Okay, everybody I hope remembers that A operating on B of ui is equal to AI operating on B of ui. Okay, so this is the statement that we are going to go back to. All right, so what do we have now? We have essentially A acting on
Next
B.
page, ma'am.
Sorry. Oh yeah. I'm very sorry. Very, very sorry. Thank you for telling me. I do stupid things sometimes. So, A acting on B, we'll have to take one of these guys, okay? We'll have to take one of these guys. So, let us take BU of, let us say some R, okay? This R could be 1 to N, anything. What am I getting now? I'm getting AI, B acting on UIR, right? Now, what does it tell me? It tells me that BUIR is also an eigen function of A with eigenvalue AI. Okay, this is what I am concluding, right? Now, let us think about it. Degeneracy of AI is how much we said? Is N, right? So now let's look at it. What are the eigenfunctions associated with this AI? There is UI1, there is UI2, there is UI3, and like that UIN. And now we have this BUIR. Now, if BUIR is linearly independent of all these guys, then how much does the degeneracy become? N plus 1, right? Because already N fellows are here, plus there is one guy here, it will become N plus 1. But that's not correct. The degeneracy we have written down is N. So what is the only way out? The only way out is that this BUIR we should be able to write as some C1. Okay, I'm going to write it a little carefully. I'll write it as CR1 ui1. Remember, this r goes as this, okay, and this 1 goes with this, okay. It will be written as cr1 plus cr2 ui2 plus dot 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 crn uin. That is the only way it is going to be possible. Is this clear to everybody? Has everybody understood this?
Yes, ma'am.
Yes? More people? I can hear only one voice agreeing with me. Is
Yes,
it
ma'am.
clear to everybody?
Yes, ma'am.
That you please remember, we already had n guys. Now we are putting one more fellow because this is also there, right? So obviously, this particular guy, this guy here, we should be able to write as a linear combination of all these guys here. That's all that I have written here. Okay. So now we will do one thing. We are going to write down the situation for each of these UIs. Okay. For each of these UIs. We can do this particular, what we wrote earlier. Okay. These are all eigenfunctions of A, right? So we can write this equation for each of these UIs, right? Yeah. So we will do that now. And we will write down the linear equation. So let me just go to the next page. Okay, I will go to the next page.
Excuse me, ma'am.
Yeah.
Ma'am, can you you said UI2 can't be written in terms of C1 and UI1, but in the last conclusion you said B of UIR can be written it as in terms of
Yeah.
C.
So what I'm telling you that these are linearly independent. Okay, so let me just, can you see my mouse?
Yes, ma'am. Yes, ma'am.
1 second, I'll get the spotlight. Okay, that's better. Right. Oh, this is so annoying. Okay, so you look at these over here. Okay, there are n such eigenfunctions, correct?
Yes,
Yeah.
ma'am.
Now I have said that they are linearly independent. Why? Because we know the degeneracy is n. So they have to
Yes.
be n linearly independent
Independent.
eigenfunctions. Which
Yes,
means
ma'am.
if I pick up any one of them, let us say I pick up ui3. Okay.
Mm.
This ui3 I cannot write as a linear combination of the others. That is what I'm trying to tell you over here. Okay.
Mm.
That is the meaning of linear independence. That I cannot take one of them and write them as a linear combination of the others.
But with the
Now,
operator we can write it.
sorry?
With the operator we can write in terms of C terms, no? Like
I
B
don't.
is the operator.
Yeah. Huh. So just let me just come to the thing. I think you've got the idea right. Okay. So now what has happened? I have ended up with this equation, right? You remember we have derived
Yes.
this equation already. We know that A acting on this BUIR is equal to AI BUIR. Okay. Yeah.
Yes, ma'am.
So obviously this BUIR is again an eigenfunction of A and it has got an eigenvalue AI. All right.
Yes, ma'am.
Now, what is the basic thing? The basic thing is that already these fellows are there. This UI1, UI2, UI3, UIN, which are the n linearly independent eigenfunctions of A.
Yes.
Additionally, now I also have this equation, means this is also an eigenfunction of A, correct? With eigenvalue AI. Now the question is this BUIR a new eigenfunction? Which means that it is linearly independent of these n guys, or it is actually not a new eigenfunction, it is some combination of these guys. Suppose now I say it is linearly independent, it's a new eigenfunction. Then what happens? There are already n of them, plus now there is 1. So there will become, the degeneracy will become n plus 1, which we know is not correct. We know degeneracy is n. Then what is our choice? Our only choice is that this BUIR, I must be able to write it as a combination of these guys. And that is what I have written here in the last statement. Do you understand?
Yes,
It
ma'am.
is
Yes,
not
ma'am.
linearly independent of this. Thereby, I can have this equal to over here. This,
Yes,
on the other hand, is linearly independent of all these other guys. That's why I cannot write it as a linear combination. Is this clear?
yes, ma'am. Thank you.
Any other doubts, please? If there are other doubts, please ask. I will explain. Because otherwise the next step you will not understand. Is this clear?
Yes, ma'am.
Okay, good, good. Thank you. Thank you, Lavanya. Right. So let me go on to the next page now. And let us write down all the just one second. So if you remember, we had what? We had for this AI, okay, what were the n linearly independent eigenfunctions? Independent eigenfunctions. There were ui1, ui2, all the way to uin. Correct? So now I can write bui1 as equal to, this will be, just one second, c11 ui1 plus c12 ui2 plus like that c1n uin. Okay, I'm writing down the first equation. Okay, we have agreed that B operating on any of the ui's will be a linear combination of all the other ui's. Okay, the same argument which I used earlier there. So only differences, please note, I had written it for R. Okay, here I'm putting the R as 1. Okay, please look at it. I'm putting the R as 1. All right, that is all that I'm doing. Now I can write it for BI2. So here R is 2 now for me. Okay, so again I can write it as C21 UI1 plus C22 UI2 plus like that C2n UIN. Okay, like that I can go on, and finally I can write BUIN is equal to CN1 UI1 plus CN2 UI2 plus dot 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 CNN UIN. Okay, I've written down all the equations. Okay, so now we can write this in matrix form. Okay, how do I write it in matrix form? I can write it as like this, that B operating on just UI1, UI2, like that till UIN, okay, is equal to C11, C12, C1n, C21, C22, C2n, CN1, CN2, CNN. Okay, I'm just writing the whole thing in UI1, UI2, UIN. Everybody agrees with this? I've written this set of equations in this matrix form. Has everybody got it?
Yes, ma'am.
Is it clear
Yes,
to
ma'am.
everybody? Any doubts, please? Everybody's good with this? No problems? Hello?
No, ma'am.
Yes, ma'am.
Okay, good. So you can see, right, that this set of equations which I have written here, this will become like this matrix form. So I can say that I can write this B as this square matrix, which looks like this. Okay, correct? C11, C12, C1n, C21, C22, C2n, Cn1, Cn2, Cnn. Okay. All right. So I can write this B as this square matrix. Okay. Now let us think about a little more abstract, all right, form. Let us imagine the vector space. Okay. Now what is this doing? This is describing for you all possible dynamical states of the system. Okay. All dynamical states of the system. Inside this, I am going to define a subspace. Okay. What is this subspace made out of? This subspace is made out of all linear combinations. So all linear combinations of ui1, ui2, like that till uin. Did you understand this? You have a full vector space. Now you take out these linearly independent vectors, these n linearly independent vectors, ui1, ui2 up to uin. Okay, take them. All linear combinations of these will form a subspace. Okay, has everybody understood this concept that it will form a subspace?
Yes, ma'am.
Okay, now let's imagine, let's pick up one of these guys, okay, from the subspace. How will I be able to write it? Let me just go here. Okay, so any member of this subspace, any member of the subspace, so, okay, any member of the subspace, I should be able to write it as some d1 ui1 plus d2 ui2 plus dn uin. Okay, any member of the subspace will be a linear combination of these guys. All right. Now, what you have to realize that this BUIR, okay, this BUIR, okay, is also belonging to this subspace, correct? Because I can write this BUIR as a linear combination of this, so it must be belonging to the subspace. How many of them are there? There is 1, there is 2, there is up to n. So there are n members of the subspace which are nothing but these BUIRs. There are n members of the subspace which are basically BUI1, BUI2, like that till BUIN. Okay, has everybody got it? There are n such members which are essentially these. Everybody got it?
Yes, ma'am.
Yes, ma'am.
Okay.
Yes, ma'am.
All right. Now what we are going to ask is now, let us imagine we have some other members. Okay. So like these are n in number, right? So question I'm asking, are there n other members of the subspace such that, okay, so let's give these members some name. Okay, so we will call them some phi1, phi2, phi3, okay, phi n. Okay, so these are also belonging to that subspace, but now there is a crucial difference between them. What is that difference? They are such that B operating on phi 1 will be giving me some B1 phi 1. Okay. B operating on this phi 2 will be giving me B2 phi 2. Okay. I am asking whether there are such members. Okay. Now I'm going to expand this. All right. I'm going to expand this and write it out more clearly. All right. So what am I going to do? I'm going to write it as B phi 1 is equal to B1 into phi 1 plus 0 into phi 2 plus 0 into whatever phi 3 is there, dot dot dot, plus 0 into phi n. Okay. Similarly, I can write this B phi 2 as equal to 0 into phi 1 plus B2 into phi 2 plus 0 into phi 3 plus dot 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 0 into phi n. I can continue and I will write this as B phi n is equal to 0 into phi 1 plus 0 into phi 2 plus 0 into phi 3 plus Bn into phi n. Has everybody understood this? I have written these equations only. I have written it in an expanded form here. Has everybody understood this?
Yes,
Yes,
ma'am.
Let me
ma'am.
now write this in a matrix form. Okay. This one, I am going to now write it in a matrix form. How does that matrix form look? B into phi 1, phi 2, dot dot dot, phi n is going to be equal to B1 0 0 0 0 B2 0 0 0 0 B3 0 0 0 0 Bn into phi 1, phi 2, phi n. Everybody agrees with me?
Yes, ma'am.
Okay. What is the form of this matrix? What you will realize that it is diagonal. What do I mean by diagonal? Only the leading diagonal members. Leading diagonal means starting from here. Okay, starting from here. You can also have something starting from this position and going till here, but that's not the leading diagonal. Leading diagonal is when it goes from this position to this position. Okay? Yeah? So only the leading diagonal members are non-zero. Everything else is a zero. So this is a diagonal representation. And just like I showed you earlier, it means that this B can be written in this diagonal form. Correct? It can be written as B1, 0, all the way till 0, 0, B2, 0, 0, 0, Bn. This is also B. Correct? So please note, here we had a representation for B. Correct? Here, this is also correct. And we had a representation for B here. This is also correct. So the question is, all right, so the important question is, I'm going to change paper. What you need to carry out is a diagonalization process. Okay, so can B be diagonalized? Can we do it? And if it is going to be diagonalized, okay, will it change the physics of the situation? See, it's not good enough for us to do just the math, right? Maybe mathematically you can make it a diagonal, no problem. But it should not change the physics. Because please remember, every member of this subspace represents for us a dynamical state of a physical system. So it's not that you can do any kind of mathematics, add, subtract, divide, jump around, okay, Fourier transform, whatever you feel like, and diagonalize it, okay, to have it lose its physical meaning. That's not possible. Physics does not allow it. So the question is, can B be diagonalized? And is it legal? What do I mean by legal? Not like going to court to the judge as we do, but physics wise, is it legal? And the answer is actually yes. You can do it using what are called as unitary transformations. You can do it using unitary transformations. Okay. And so two things now. I will first put up what is called as the fundamental, just 1 second. Yeah. So I'm going to put up a fundamental theorem of matrices. I'm not going to prove this for you. It should have been done for you when you did your BSc course on matrices. Okay. So I'm just going to state it over here. What does the fundamental theorem of matrices say? It says that any Hermitian matrix, any Hermitian matrix can be diagonalized using unitary transformations. Okay. Now, is B a Hermitian matrix? We know it is a Hermitian operator. Why do we know it's a Hermitian operator? Because we started off saying that A and B are observables. If they are observables, please remember all the properties. And one of the properties is that it is Hermitian. So yes, B is an Hermitian matrix. All right. Next thing, yes, is there some question? Any question? Okay, so we know B is a Hermitian matrix. Why? Because B is an observable. Okay, please look up the properties of an observable and you'll realize that one of the properties that it is Hermitian. Next is that it can be diagonalized. It can be diagonalized and you can diagonalize it using unitary transformation. I am not right now, please accept me as a word of faith. I am going to prove it to you. Okay, we are going to do unitary transformations after this. That unitary transformations are physics-wise legal. Okay, they don't change the physics of the situation. Unitary transformations do not change the physics of the situation. Where is the connection with unitary transformations that you've come across already? You have met something called a unitary operator, right? The unitary operator is going to be used for unitary transformations. And unitary transformations do not change the physics of the situation. Unitary transformations can diagonalize a Hermitian matrix. So you have B, which is in a non-diagonal form here. Where is this non-diagonal form? Let me go back a few 2 pages. This is the non-diagonal form. Okay, this is the non-diagonal form. This is the non-diagonal form in this subspace, right? What you can do is you can use a unitary transformation and you can take it to this kind of a diagonal form. All right, you can take it to this kind of a diagonal form. So you can go through a unitary transformation, which is physics wise legal. The physics does not change in a unitary transformation. I will prove it to you. Okay, and you can go to B in a diagonal form. So now let us look at the situation. You had your vector space. In that you had a subspace. What was the subspace made out of? Linear combination of ui1, ui2, uin. So here you found n other phi i's. And what is the property of these phi i's? Such that b phi 1 is equal to ai phi 1. B phi 2, sorry, not ai, sorry, my bad, is equal to b1 phi 1. B phi 2 is equal to b2 phi 2. B phi 3 is equal to b3 phi 3. And like that, b phi n is equal to bn phi n. So these phi's are eigenfunctions of B. Okay. Question that you can ask is that what about A? Okay. So the answer is this. If you operate A on, say, one of these phi i's, let's take a particular number. Let's take phi 2. We know that this phi 2 belongs to this subspace, which means we should be able to write this phi 2 as a d1 ui1 plus d2 ui2 plus some dn uin. Okay, why? Because again, as I told you, this phi 2 belongs to this subspace. Okay, it belongs to this subspace, and everything in that subspace is a linear combination of these, right? So now let us see, what will you get then? D1 AUI1 plus D2 AUI2 plus DN UIN, which is going to be D1. What is A acting on UI1? We know it is nothing but AIUI1 plus D2 AIUI2 plus, like this, you will get, sorry, here also you will have an A, you will get DN AIUIN. Take the AI common. Okay, I'll have to write it in the next page. I'm sorry. So what are we doing? We are doing A acting on phi 2. I will take out the AI common and you will get D1 UI1 plus D2 UI2 plus dot 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 DN UIN. Okay, this is going to be
Ma'am,
AI.
it's A phi I2, right?
Sorry.
The starting A phi I2, right? Or the 2 only, ma'am? A phi
Yeah,
I2.
A phi 2. Okay, because this is phi 2, right? Here, phi 2.
Ma'am,
I'm
like in
putting
the
a
next
phi 2. I'm
page, you
putting
wrote
some
A
steps.
phi. 2 only.
What did I write?
The next page you wrote A52 only, the starting one.
Yeah.
A5I2, no?
No, Baba. It's this I made a mistake. Look at
Okay.
this. This is phi 2 only, right? There is no
Yeah.
AI phi 2.
Okay, okay.
Okay. There's only
Yes,
a phi 2. There's a phi 2 here, right? Look at where
okay,
my
ma'am.
cursor is. This phi 2. So I'm doing A
Mm-hmm.
on phi 2. But this phi
Okay.
2 itself can be written as a, so this I am putting 2.
Mm-hmm.
I am putting as 2. So I'm writing it as A phi 2. Is that clear?
Okay, ma'am.
Yeah. So this is not an I. I just made a mistake over there. Okay.
Okay, ma'am.
Scratched
Okay.
it out. I'm sorry. All right. So this A phi 2, okay, this A phi 2 is equal to, so this AI will come out common, but what is this linear combination? This is nothing but phi 2. Okay. So therefore, phi 2 is an eigenfunction of A with eigenvalue AI, right? And phi 2 is also an eigenfunction of B with eigenvalue B2. So is this clear now? So by doing this, what do you call it? This diagonalization, you have ended up from this subspace, you have picked up n other members which are eigenfunctions of both A and B. And you have done it using unitary transformation, which do not change the physics of the situation. Is this clear to everybody?
Yes, ma'am.
Has everybody understood it? Now,
Yes, ma'am.
what is the conclusion thereby? That if A
Next page,
and
ma'am.
B,
Next page, ma'am.
sorry. Thank you. I don't know why I do such stupid things. Yeah. So basically what you realize is that if A and B commute, then every eigenfunction of A is also an eigenfunction of B. Of course, as I told you, we have hidden some things away in this. Okay. We have hidden away the fact that we may need to do a diagonalization process. But finally, we can get eigenfunctions, which are eigenfunctions of both A and B. So, if AB commutator is equal to 0, which means A and B commute, then A and B share a common set of eigenfunctions. What had we proved earlier? We had proved that if A and B have a common set of eigenfunctions, this was the earlier proof, right? This we just proved now. This is the earlier proof. If they have a common set of eigenfunctions, then they commute. Correct? So now we realize that this is proved, and it is proved by. If A and B commute, they have a common set of eigenfunctions. If they have a common set of eigenfunctions, they commute. Okay? So this is proved and proved by. So now we are not going to really bother to say it. If I tell you that A and B commute, immediately you should know they have a common set of eigenfunctions. If somebody tells you, hey, A and B have a common set of eigenfunctions, you should immediately know that the commutator of AB will be 0. Okay. Now, why are we paying so much attention to this? What is the significance of this? It essentially means that if AB is equal to, this commutator is equal to 0, it means that you can pick up a wave function. If it is an eigenfunction of A, you will get some A psi, and it will also be an eigenfunction of B, you will get a B psi. What it tells you is that you can do simultaneous measurements of dynamical variables linked with A and B. Okay, it tells you that we should be able to do simultaneous measurements of dynamical variables linked with A and B. So the moment I tell you that, hey, A and B commute, you should immediately know that I can measure variable connected with A and variable connected with B precisely simultaneously. What does simultaneously mean? At the same point of time and precisely, no problems. And this is very important. Now you obviously know that position and momentum do not, what is the problem with them? You cannot precisely measure them simultaneously, right? You know that. Now in this context, what does it tell you? It tells you that position operator and your, what do you call it, the momentum operator, of course, x and px, this will not be equal to 0, which means they will not commute. And this whole thing you know as your uncertainty relation, right? You know this as your uncertainty relation. I don't know whether you've already proved this with Meera ma'am, that this actually is equal to IH cross. But right now, from what I have explained to you, you will immediately realize that if you take X and if you take PX, or you can take Y and you can take PY, right? So you have the position and the momentum in the same direction, and you will realize that they cannot commute, because if they commuted, you should have been able to measure them precisely simultaneously at the same point of time. Okay, but you cannot do it, so which means they do not commute. Okay, so what is the time now? Because after this, what we will do is we will have to derive the generalized uncertainty relation. Okay, so we will derive the generalized uncertainty relation, and you will understand what is the most like general way in which you can express an uncertainty relation, and how do you actually quantify or calculate an uncertainty. Okay, so these things we will do in the next class. So I'm going to stop the share now and ask you whether you have any doubts. So are there any doubts, please? Any doubts, please? I know it has been please try and picturize it. I'm going to put up these two lectures in the, what do you call, in the folder that we have already got up. So you will be able to see the full recording. Try and understand it if you have doubts. Okay. In case you have more doubts, we will definitely take it up in the next class. All right. And yeah, we will move it from there. So any doubts, please, right now? Outstanding doubts, anybody? Fine. In that case, we will call this class to a close and we will meet each other, I presume, next Thursday. I don't know whether a new timetable will come out. Yeah. So take care. Stay safe, everybody. Cases are going up. COVID cases are really climbing like crazy. I hope you're all safe at home. Stay safe, take care of yourselves, take care of your family members, and we will see each other next Thursday. Okay? So have a very nice evening, all of you. Bye then.
Bye, ma'am.
So I will end the meeting now. Okay?